3.1, Matchings and Covers. So for this section, just as the name implies, we're going to talk about matchings, we're going to talk about covers, we're going to talk about what types of matchings and covers are we interested in. And in this section, we're also going to go ahead and introduce a named theorem, and I'm going to provide a very rough sketch of the proof of that named theorem. So let's go ahead and get started. First thing we got for today is a vertex covering. So a vertex covering of some graph G is a vertex subset such that every edge of G is incident to a vertex of S. In other words, if I look at any edge, every edge in fact, of G, it must be incident to at least one of my vertices in S in order to be considered a vertex covering. So if I do have a vertex covering S, then you're going to hear me say sometimes S covers the edges of G, or the edge set. Or even more simply, S covers G. So we have a vertex covering. For my next definition, I have an edge covering. And this is probably what you might expect it to be. We have pretty much the same idea for our definition, but with edges this time. So an edge covering of my graph G is an edge subset such that every vertex of G is incident to an edge of B. So again, if I take all the vertices of G, each one has to be incident to at least one edge of my edge covering B. And similarly, if I do have an edge covering, you're going to hear me say B covers the vertices, or B covers V of G. Or more simply, B covers G. So let me go ahead and show you an example real quick. So here I have on the far left my graph G. I drew this randomly. In the middle, notice I've highlighted these edges. I've highlighted this one on the far left, this one on the top right, and this one sort of on the bottom right as well. I claim that this is an edge covering. I selected a group of edges, and every vertex in this graph is incident to one of my edges. And we can verify that very quickly. If I look at each of my 5 vertices, it's incident to one of my highlighted edges. What about here on the far right? Here I've selected 4 vertices. So if I look at these 4 vertices, is it true that every edge in my graph is incident to at least one of my vertices? Looking through it very quickly, we should verify yes. For example, on the far left, this is incident to this vertex. These 2 edges are incident to their respective vertices, and the rest of these are also incident to a chosen vertex as well. So here I have a vertex covering. So we have a vertex covering and an edge covering. One question that some people might ask in other problems is saying, what's a minimal vertex covering or a minimal edge covering? Which is always a nice problem that we can think about in the back of our heads. So now that we have an idea of what the coverings are, let's go ahead and talk about a matching in particular. What's a matching? That's the other part of the title of this section. So let's say that I have an edge set and call it M. M is a matching in a graph G if it is a set of non-loop edges with no shared endpoints. And this is a little bit of an odd definition to think about, but I promise it's going to make a little bit more sense once we start seeing some examples here. In other words, a matching is a group of edges that are standing alone. So if I have a matching, the vertices that are incident to the edges of a matching M, we say that those vertices are saturated by M. Whereas the vertices not incident to the edges of M are unsaturated. And just for it to make this sound a little bit quicker, we often say vertices are M saturated or M unsaturated. So again, this is a nice terminology, just simply stating, is my vertex incident to a matching of an edge of my matching of M. And then I have a perfect matching. A perfect matching is a matching that saturates every vertex. So I've been bringing up these definitions, and it's a little bit abstract or maybe a little bit hard to interpret initially, but let's look at this example. Once again, I have 3 pictures. Here on the far left, I drew some random graph. In the middle, I've highlighted 2 edges, and I'm going to call those 2 edges to be the edge set M1. I claim that M1 is a matching because it matches my definition. It's a set of edges, they are not loops, and none of my edges have the same endpoints. In other words, my edges are not connected to each other. You can see here, these 2 edges, they do not share any of the same vertices. If I look at this middle matching, this is not a perfect matching. Remember, a perfect matching says that I saturate all my vertices. So I may look at this middle picture or graph and say, is every vertex saturated? And again, saturated just means that it's incident to one of my edges. So if I look at this middle picture, these top 4 vertices are saturated. They're incident to an edge. But these bottom 2 are unsaturated. They're not incident to the edges I've selected here. Since I have some vertices that are unsaturated by M1, I may have a matching, but it's not a perfect matching. But let's look at this last one on the far right, M2. Here I have 3 edges. This top one, this one on the bottom left, and on the bottom right. And if I look at this, this is definitely a matching. None of my edges share a common vertex. And furthermore, all 6 of my vertices are saturated by this matching M2. Since every vertex is saturated, then I have that M2 is a perfect matching. Every vertex is covered. Another way that someone might say a definition for a perfect matching is a matching that covers all the vertices of G. Or you might even just say a perfect matching is an edge cover of my graph G. That is still a matching, of course. So we have the definition of a matching. So I mentioned this a little bit earlier about being minimal, maximal. One common question is, how do I know if I have a maximum matching or a minimum vertex cover? So this brings us into one of our theorems for today. So we won't be proving this. We'll discuss it a little briefly about what this theorem means. So theorem 3.1.2, this by Koenig and, forgive me if I'm pronouncing this wrong, Egavari, regardless, both in 1931, I believe, stating that if G is a bipartite graph, again, bipartite means that I can partition my vertices of G into 2 sets that are independent. So if I have a bipartite graph, or a bigraph, then the maximum size of a matching in G is equal to the minimum size of a vertex covering. So why is that true? Let's do some just very light investigation about what this theorem, how it might be proven. So suppose I have a bigraph, and let's call those parts of my bigraph X and Y respectively. And let's suppose I have a matching, a maximum matching, for example. So remember, in a bigraph, I have 2 sets of vertices that are independent. In other words, if I look at any pair of vertices in X, there is no edge between any pair. In other words, if I have any edges, it has to be from X to some vertex in Y, but not within the same set. Same thing applies for Y as well. So here I drew some random lines arbitrarily, and let's say that I have a matching. Here I'm denoting it with these dotted thick blue lines. So what's happening here? Let's say that this is a maximum matching, and maximal if we want to be exact. If this is a maximum matching in G, then if I look at each of these edges in my maximum matching, let's select one vertex from each one. And accidentally I did make a typo here. The circle should be up here instead. So if I take one vertex from each edge of my matching, this should cover the entire graph. It should be a vertex covering of the entire graph. Now, of course, I'm leaving out an enormous amount of details in this, but this is the broad idea about how you might even approach on how to prove this problem. Again, I did have a little bit of a picture typo. This circle should be up here. Otherwise, we have these two for us to look at. All right, so I used the word maximum matching, but I didn't really define it. But fortunately, it pretty much matches the same idea of what we've been doing for maximal versus maximum. A maximal matching is a matching that you cannot make any larger. In other words, if you try to put another edge in there, it's no longer a matching. A maximum matching with the UM, this is a matching that has the most number of edges. No matter what matching you're looking at in the graph, it has the most number of edges. So again, we're just really emphasizing this difference between maximal and maximum. So from here, let's go ahead and again, more definitions before we start looking at some of our major theorems. If I have a matching M, we want to talk about an M alternating path and an M augmenting path. An M alternating path is a path where the edges of my path alternate between edges in M and edges not in M. For example, I can consider this an M alternating path. I have a path, everything just follows in a straight quote unquote line. And I can see here the edges alternate from being in M and then not in M. So this is an alternating path. If I add the extra condition that the last two edges, so the one in the beginning and the one at the end, such that the endpoints are not saturated by M, we have an augmenting path. So for example, what I have here. Very similar picture, but notice my first edge and my last edge, these are not in M, giving me an augmenting path. So this definition of an augmenting path is going to play a huge role for us later on. So again, we have our alternating path and augmenting path, some more nice definitions. One reason I did want to introduce this is that a very quick lemma that I'll introduce. Again, I won't prove this. This is by Berg from 57, so not too long ago, actually. A matching M in a graph G is a maximal matching in G if and only if G has no M augmenting path. So again, I'm just going to state this theorem. I'm not going to go too far into it, but it is a nice theorem lemma to look at. The theorem I wanted to introduce and spend a lot of time on is Hull's theorem from 1935, which states if I have an XY bigraph G, it has a matching that saturates X if and only if for any vertex subset of X, let's call it S, the cardinality of the neighborhood of S is greater than or equal to the cardinality of S. So a lot to take in here. So I'm going to go ahead and just provide a little bit of a proof sketch here. So this is an if and only if statement. So we need to prove the forward direction and then the backward direction. So for the forward direction, we're going to suppose that I have an XY bigraph with a matching M that saturates X. So let's go ahead and let S belong to X. Again, in my proof, in my statement, it says this should work for all S. So I'm just choosing an arbitrary S. I'm not specifying it, I'm just saying I have some vertex subset. If I want to prove this forward direction, I need to show that this inequality does occur. So, since X is saturated by M, then S is saturated by M. Again, remember, S is a subset of X. So if X is saturated, S needs to be saturated as well. That tells me that for each vertex in S, there is a unique neighbor in Y that in fact follows along M. So again, S is saturated, which means each vertex has an edge incident to it along M. Using that idea, we should be able to say that the neighborhood of S, its cardinality, is at least the cardinality of S. Let's go ahead and explain that a little bit nicer. How did I make that conclusion? So here I have just an arbitrary XY bigraph, and I have a matching, such that all of the vertices of X are saturated by M. Again, this means that each vertex of X has an edge incident to it from M. So if S is some arbitrary subset, such as what I've drawn here, then it has to be saturated by M, and each vertex of S has a unique neighbor in Y by following M. It could have more neighbors, but we know that there's at least one neighbor overall. So that means a cardinality of S versus the cardinality of the neighborhood. We know that the neighborhood has to be at least the size of S. And this is us proving the forward direction, and this is often what people call the quote-unquote easy direction of this theorem. The backwards direction is a good bit more complicated. Again, I'm just going to very briefly touch on it. So, for the backward direction, what I'm actually going to do is I'm going to prove the contrapositive. That is, if the XY bigraph has no matching that saturates X, then we have this condition. The neighborhood of S, its cardinality, is strictly less than the cardinality of S for some S subset of X. So remember before we had for all S subset of X, we want to show that this condition occurs for at least one set S. So let's try to prove this very briefly. Again, I will be leaving out a lot of details since we're just doing a sketch here. So if I want to prove the contrapositive, let's suppose that there is no matching that saturates X, just as we have here for our initial assumption. What we're going to do is we're going to let U be within X such that we are not saturated by M. Again, X is not completely saturated, so there must be at least one vertex that is not saturated. And we're going to let S be all the set of all vertices in X that can be connected to U by an M alternating path, and T be the set of all vertices in Y that can be connected to U by an M alternating path. Lots of terms here, but let's draw a picture. So I have X and Y, again my sets, and then I'm saying that since X is not completely saturated by M, there's at least one vertex U where there's no edge in my matching. So I let S be the set of all vertices that can be connected to U by an M alternating path. In other words, let's look at this one for example, this third vertex. If I go along M, I can go back to U via an edge that is not an M. So again, I'm swapping back and forth between M and not M. And this occurs for all of these vertices I've drawn here. For example, the second one. This is along M, not an M, along M, not an M. I got back to U. And then T is a similar idea, but these are the vertices in Y that I can reach to U by an M alternating path. So for example, this middle vertex in T, I'm actually directly connected to it. Technically, this is an M alternating path. Same thing for if I want to start with this first vertex. I start off with not an M, back in M, not an M. So here we have S and T. Clearly, U has to belong to S because, well, a vertex is connected to itself by a trivial path. So the claim here that I'm going to make is the matching M matches T to all of the vertices of S except for U. In other words, with the exception of U, all the other vertices, there's a matching, an edge in my matching that connects from S to T. Just like here, each of these vertices can be matched or connected to a vertex in T via one edge of my matching. So this claim, again, it's a little bit complicated. If you do want to take a look and try to prove this is a really nice claim that you can try to prove. But let's say that that claim is true. If that claim is true, then the size of T should be the size of S minus U, which is equal to the size of S minus 1. Furthermore, since T and S minus U can be matched via bijection, then we know that T is a subset of the neighborhood of S. So in other words, S may have more neighbors, but we know that T must be a subset. And the last thing I'll note about this, again, leaving out an enormous amount of details, as it turns out, one thing that can be proven is that T is, in fact, the entire neighborhood of S. And proving this would actually complete the proof. So in a very rough proof sketch, I left out a bunch of details, but this is the overall idea on what we might be looking at to prove Hall's theorem. So I do the complete proof is included in the notes that I gave y'all. I do recommend that y'all take some time to look over it. But besides that, that's all for this lecture video.